Hi, I'm LVH, and I'd like to talk to you about a project I've been working on called icecap. Icecap is a modern object capability system using URLs. So in other videos, I've been talking about what capabilities are and why you might want them, how you actually use capabilities in general, and icecap in the specific. But in this particular video, I'd like to delve a little bit deeper in the cryptographic backings behind icecap. Now, I'm not going to talk about the obvious things like all of the links that carry sensitive information are TLS all of the time. That kind of thing is obvious, but there is crypto beyond TLS in IceCap, and so I'm going to talk specifically about that. So as a quick overview, caps are symmetric keys. They're very long, 256 bits, which means that even if somebody manages to come up with a extremely large quantum computer, we should still be fine. And they're cryptographically random, obviously. And key derivation produces other keys which are used internally by IceCap, which is the index into the database and the blob encryption key. And it should become apparent in just a sec when I explain the larger overview of how these bits fit together, what exactly those things are and why it's important that they're derived from other keys. IceCap uses modern crypto exclusively. For example, as a CSPRNG, it will only use a native PRNG, so that means urandom or CryptGen random, depending on which platform you're on. It does use that through the secure random, and that's a Java class, but still you're getting bytes straight out of wrandom, so you can't get all sorts of nonsense like a user space CSPRNG, which could be poorly seeded or unseeded or keep the same seed across forks or other nonsense like that. It just sidesteps all of that and only uses wrandom. The cryptographic backing is mostly provided by libsodium. So it uses a KDF, specifically it uses Blake 2 in keyed PRF mode. And for message encryption, it uses SecretBox, which is a fixed authenticated encryption system using XSalsa20 and Poly 1305. So these are pretty conservative. They're basically the most modern things that you can do while still being extremely conservative and having only pretty much trusted algorithms. The only surprising thing perhaps is that there's no HKDF, and that's a good question, but why? Well, first of all, what does HKDF give you? It gives you an extraction phase where you give it a bunch of bytes as input and it extracts entropy from that. Now, that's not necessary in our case because the input is going to already be a cryptographically random key, so there's no point in having the extraction phase. Now, the RFC for HKDF specifically mentions that there's a lot of cases where that could be that you already have cryptographically random input and that you can simply skip the extraction phase. So that in itself is not a reason to not use HKDF. The other thing that HKDF gives you is an expansion phase, so where you turn that input, or at least that the entropy gathered from the input, into a bunch of keying material for the output. In our case, that's not necessary because actually Blake 2 provides ample output by itself. By default, it's like 512 bits for Blake 2b that come out, so it's actually exactly enough for what we need. And then finally, HKDF is good because it gives you info and salt parameters. And it turns out that Blake 2 provides those as well. So again, basically all of the features that made HKDF great were considered when designing Blake 2, and as a result, it's not actually necessary for us to use HKDF, but that's specifically because we're using Blake 2. If we were using a different, perhaps an older hash function, such as SHA-256 or whatever, then we would obviously be using that in an HKDF construction. But specifically because Blake 2 provides a PRF mode, this is not necessary. Future crypto options, for example, could be Buddy, which is a closure binding around Bouncy Castle. The obvious benefit for that would be that it would be all JVM. You could just get a single jar. Whereas right now, because we're depending on libsodium, that means that you have to have a shared object laying around. That shared object is not yet packaged for Ubuntu, or at least a sufficiently recent version is not packaged. And as a consequence, it's kind of tricky to install. We can possibly fix that by shipping Docker containers, but then you run into the problem of shipping security-sensitive software on Docker containers. So in general, I'd like to avoid that. Of course, the JVM is not a panacea either. Short version, this is a tricky problem, and it is an open question. Bouncing Castle does have Cha-Cha 20 and Poly 1305, so that's more or less equivalent to Xsalsa 20, and Poly 1305 exists in Libsodium. The biggest difference is the non-size, which we don't care about. The only problem is it doesn't have Blake 2, so we'd have to do the HKDF, probably HKDF SHA-256 version. So maybe we'll look at some HSM support as well, particularly for runtime hardening. I'm increasingly convinced that you can't actually write secure software, not even in C. And of course, then it becomes kind of tricky. This also ties into a recent point made by Colin Percival that even zeroing memory is not actually good enough because modern ISAs will leak stuff all over the place, and modern compilers are really, really good at figuring out that the zeroing ostensibly doesn't do anything, and therefore it can skip it. So yeah, very, very tricky. I think this is definitely not a problem that we have to solve specifically for icecap. Icecap just works under the assumption that there exists somewhere a secure authenticated encryption scheme and a secure key derivation function. As long as we can somehow use that, we're fine. So this is an overview diagram of, this is when I told you earlier about how all of the pieces come together. This is a diagram that does that. It's kind of noisy, and I do apologize for that, but I'll walk you through it, and hopefully it is not too bad. So we're going to start pretending that we're going to exercise a capability, right? So we have a capability URL, you get on that URL, and then it does something. So for that, we're going to start here with the cap, and first thing that happens is that goes into the key derivation function, which is configured with a seed key. So that's the key that produces that, so this is a secret key, which is part of the icecap installation, and a salt, which is not necessarily secret, but can be secret. The key derivation function produces an index, which is basically the location in the database where you're going to store the encrypted blob, and a cap key, which is used to actually encrypt a blob. So a blob is the encrypted version of a plan, which I described in another video what that is. That's essentially a description of what you're going to do when you exercise that capability, which will then later be executed, and the executor talks to a bunch of services. So the important thing to remember here is that the capability key here and the index are ephemeral. So they're basically only generated when you need them and when somebody shows up with a cap. And perhaps the most important part is that the cap itself is never stored within icecap. So we just give this to the user, and then we don't know about it. Like, we don't store it anywhere, it's just not used. And that's very interesting because that means that even if we wanted to, like, we have no way of knowing where things are stored in the database, let alone what key they're stored with. So we have fairly strong cryptographic guarantees. Another way to think about it is if you consider this as a dependency graph. So in order to know about a thing, you have to know about all of the things that have arrows pointing towards that first thing. So for example, in order to have access to the plan, which is that plain text description of what you're going to do, you need access to the blob, which is the encrypted version of that plan, and the capability key, which is the key used to encrypt that, right? But in order to get to the blob, you need the index, because without the index, you don't even know which blob we're talking about, right? But in order to produce either the cap key or the index, you need and the cap and the seed key and the salt. Why is this important, and what do these colors mean? The colors tell you where something lives. So yellow in this case means in the key derivation part. So cap key and index are ephemeral parts of the key derivation thing. Seed key and salt are non-ephemeral parts, which is why they get solid lines around them. Cap is in red because the user stores that somewhere. And the blob is in blue because the database stores that somewhere else. Now, the nice thing is that if you think about this and you consider the case of what happens if an attacker, let's say an attacker gets all of our configuration data, so that's the seedkin salt, and gets all of our database, which is all of the blobs, right? Then still there is no data leaked because you can't do anything without getting this cap. So even if you have everything else in this triangle, you can't get you can't get to cap key, you can't get to indexing, you certainly can't get to plan, which is where you presumably want to be. Um, that of course that's only an offline security guarantee. As I mentioned earlier, it's pretty tricky to actually write secure software. Um, so this does not cover all sorts of cases like what happens if an attacker manages to execute some code in your running process and somehow manages to tap into all of the JVM internals and figure out where you're storing all of these byte arrays. Um, that's tricky. That's an unsolved problem. So please don't interpret this as saying like there's a strong security guarantee that it's never going to go wrong in practice. It's just that at least from a theoretical level, we have very strong guarantees, and then on top of that, we need runtime hardening. But at least the theoretical basis is quite strong. And that's it. And I look forward to your questions and comments. Thank you for listening.